Welcome, chemists. Today, I'm going to talk about an activity series, and I have brought my good friends, the alkali metals, and I am going to put them in water, and we're going to see some exciting things. So the deal with alkali metals, you may not associate them with metals because they don't necessarily get a lot of publicity, but I have lithium here, and I have sodium, and I have potassium, and I have pure samples. What's cool about our chemical company, where we can order all of our supplies, is that you can actually obtain pure samples of each of these, and you can see that the lithium, it is metallic. It's very hard to purify, and you will not see it in this state in nature, and you're going to see why in just a second, because it is very reactive. But it does have all the properties of the metal. One of the cool things about it is you can actually cut it with scissors, which is just the way it is. It's just a very soft metal. So I am going to put it in some water because it does react with water in its pure form. And when I put it in here, I've got this petri dish filled with water, and I have put a couple drops of phenolphthalein, which is an acid-base indicator, and you're going to see why, hopefully, in a second. Hopefully it will show up. And when I pop it in, you will start seeing a reaction. You will see some bubbles forming on the surface of the lithium. There's a pink color that is starting to form, starting to get stronger. And it's producing a gas, which if you were in the room right now, you might be choking on it if you were close enough. And you can see that it's continuing to react, and it will continue to go as long as there is a solid piece of lithium inside. It's bouncing around, it's hitting the sides, and it is slowly getting whittled away as it reacts. Okay, and if you go to the board here, we can see what exactly is happening to the lithium. We have solid lithium with the water, so those are the two reactants. And what we have here is lithium hydroxide, and that's where the pink color is coming from, actually, because that's basic. And phenolphthalein, in the presence of a base, turns that pink color, and that's dissolved, aqueous. And then the gas that you're producing is hydrogen gas. And it doesn't smell very good. It is flammable, and it's not very nice to breathe in. So that is the reaction that we're going to see with all of the alkali metals. But if you come over here, we're going to take it up a notch. Because what we've been learning about in this unit is as you move down a group of metals, they get more and more reactive. And the reason is with my pictures right here. I've drawn the Bohr model of each element. I've skipped hydrogen because that's kind of iffy whether that's really a real metal at all. And I have lithium. You see where it's positioned on the periodic table that lithium has two energy levels that have electrons in them. The first energy level has 2, so that one's full, and the second energy level just has that one extra electron hanging off. And when this reacts with the water, it is that electron that is removed from the atom. And you saw the effects. But what happens if I move a little further down the group and go to the next metal, which is sodium, and you look at its Bohr structure, and you look at its energy levels, it looks very similar to lithium in that it has one valence, but it has an extra energy level. It has an extra shield, as we call them, which means that electron cannot feel the same pull from the nucleus. And it is actually much easier to remove that electron because of those additional shields. So let's take a look at what that's going to look like. So I have a petri dish just like before. I have samples of pure sodium. It looks a lot like the lithium. They actually store these in kerosene, so they're very oily, and that's to prevent it from reacting with water. And so when I put it in here, we're going to expect a slightly faster reaction, slightly more violent, and let's see if we get it. comes off. You can see that it's bouncing around much faster. More gas. Little snap crackle right there. And it's done. Oh, actually a small piece flew over into the lithium dish. So, yay, bam, faster. So you can see what's happening with the bigger atom, the more shields. It's much easier to remove that electron. But we can do even better. They actually do sell samples of pure potassium. This is not the same potassium that's in your banana. When it's in your banana, it's already reacted, so it's stable. But if you can purify it, you'll get this situation. One extra energy level, even easier to remove that electron, and you'll see what it does to this reaction. So I've already got a little residue in there from before, but that's not going to affect anything. Here's my sample of pure potassium. I'm going to drop this, and I'm immediately going to take 3 steps away because, yeah, these can be scary. Here we go. Okay. And started to, all right. So the first time it popped out, and yeah, you see a lot more flame, and there's still a little bit on the tabletop, so I'm just going to throw that guy in there too. Woo! Yeah, this is the one where if you were in class, we would be in the fume hood because this will shoot out and hit various things around the room. And there's all these little potassium residue, which I will wipe down with water real good because you see they still ignite. And yes, I think the point is made that as you move down a group, the atoms get larger, they get more, the metals get more reactive because it's easier to remove the electron for the larger atom. Hello chemists, I have one more demo that I wanted to show you with the alkali metals. Before we leave the matter of lithium, sodium, and potassium, I wanted to show you that the sodium chunks, and you can't get them from our chemical company anymore, but 10 years ago, they would literally send you large chunks. I've cut this one down from what was in the bottle, but yeah, this whole bottle is full of these. You could throw this in a lake, and you would have a pretty large explosion on your hands. And just to give you a sense of how large an explosion you can get with sodium, I have a large dish of water in here, and I've added the phenolphthalein because you are going to make sodium hydroxide, which is a strong base. And to make this a little more fun, I have created a little boat out of paper, and I have put several nice sized chunks of sodium inside. So I'm going to set this boat to sail on the water, and yeah, we're going to see what we're going to see. 1, 2, 3. All right, now I deliberately constructed my boat so that it will take a little while for the water to soak into it, giving me a little time to get out of there. So here we go. Oh, no. Here it goes. Here it goes. Okay. So once it gets started, it shouldn't take long. So you'll see the sodium starting to ignite, and as it does, we'll put paper on fire. And the whole thing goes off in one big firework. And that's why we do it in the hood. There you go. The reactivity of sodium with water. Mr. Coleman out.